is going to be AJ Malik and Clinton Char, talking about lessons learned on the choice of material for transmission line towers. AJ has over 17 years of diverse and worldwide experience in the electrical transmission industry. Prior to his current assignment, he served as Vice President for Trans-American Power Products and Engineering Manager for Valmont Newmark. Mr. Malik earned a BS in Structural Engineering and Construction Management and an MS in Structural Dynamics in India. He is a registered professional engineer in the state of Texas, authored numerous technical papers in transmission line engineering. Now, I understand AJ is going to be giving most of the presentation, but Clinton's going to be available for answering questions during the question period. And Clinton's been employed by Hawaiian Electric Company for 18 years as a civil structural engineer and overhead transmission distribution projects. Currently employed by Southern California Edison as a project program manager. All right, help me welcome AJ.
Good morning. Can you hear me? Very good. Well, I'd like to thank Clinton. He's so generous to allow me to present the full paper. You know, we have 20 minutes and then divide. We decided that why not I go ahead and do the presentation, and he will be answering the questions, so please be ready with the questions that you may have for him. Good. This topic is very crucial. I'm not sure that how many of you utilizing the lattice tower versus steel pole. I know steel pole is very common nowadays. But lattice tower used to be very common 20 years ago, 30 years ago, and now it's coming back again, some of the high voltage transmission line that we're dealing with. And a lot of things have changed from 30 years ago or 20 years ago. And when we come to the new phase of designing those towers, a lot of things we forget. And that's what my paper here is to address. What are the things we need to consider that we haven't thought about in the past, and why it's so critical for our reliability of the transmission line. So I'll start with the transmission pole. Transmission pole, we have a pretty set standard. I'm pretty sure all of you know that if you design a tower, a pole, then you may have the steel that is pretty set standard that you know what you're getting. So basically when you're designing a pole, then you know by spec you have your Sharpie value, which is common, which is 15 foot-pound and minus 20 Fahrenheit, and which is also applicable to pole, anchor bolts, welding, and it's very common standard. So nobody asks any questions. You design it based on your design criteria and go with it. When you go to the lattice tower, that 1097 is silenced. What Sharpie should we consider? Shall we consider for the steel or the stub angle or the connection? There's nothing on that. So now it's more common that people have a choice. So end users decide what Sharpie they need. So historically, people will say, I don't need a Sharpie. Why? Because I've been using this tower 30 years ago, tower is still standing, so why need a Sharpie? Then somebody say, yeah, you're right, let's do a number, so pick numbers, so I'll choose 15 foot-pound minus 0 degree. Or somebody pick 15 foot-pound minus 20. Somebody go even more stringent and say 25 foot-pound plus 10. So what is the real Sharpie that we need to do? And as you know, that for a lattice angle, we have a limited choice of the mill. So you don't have a plate like you go any mill you can get it. Lattice, you have only 2 or 3 mills that can give you the certain size and the length that you're looking for your project. So our goal should not be to confuse the vendors or manufacturer that every time you have a spec and you call it for different kind of chemistry, different kind of Sharpie, and you know all the Sharpie takes time for their process to implement it and test it, then they will give you the guarantee that they will meet the Sharpie. So it's very confusing. What should we consider? So we have a material spec A572, or now it is also 7 and 9. So it's very confusing for the manufacturer, very confusing to the steel mill, and of course for the customer also, that what guidelines should be going from here. So I'll start with the modern steel. So as all of you know, what's the modern steel is supply demand. Now it is, over global demand. So the steel mill, obviously, to make more profitable, they modify their system. So now they have a scrap-based steel, as roll conditions, electric arc furnace, which is quicker and faster, continuous casting. Again, all these things for their supply and demand. And most important thing I put on the red is silicon kill, which is very critical for pole that we have certain guidelines, but that is no guidelines. So silicon kill is most common for lattice angle. Aluminum keel is very less common because it's more expensive for them. Then also the varying combination of macro alloy they added based on the, what grade and what yield strength that they normally try to achieve. And then of course low carbon, high magnesium, they have a lot of several foreign stingers to get that certain requirements. So it's very important to specify the right requirement according to the material properties, ductility, toughness, through thickness, weldability, and of course, don't forget about galvanizing the duct, which is not as pretty common. Also, the expectation of our utility client that there has to be certain finish and certain things. So those are the things very critical for us. Unless we don't know all this, what the mill is doing, we cannot address it. So normally, a typical transmission tower, as all of you know, that combination of steel. So structural angles, I think 78% more or less. Steel plates 10%, fasteners, zinc, galvanizing. Of course, we need to galvanize that. The most common steel that we normally use is A570-250 is the most standard common. Also A36, but 60 is very rare case that we use for our lattice tower. As a fabrication process, we all know that when we do any manufacturing process, welding is very limited, but most of the equipment being used is CNC, and then with the CNC machine we do drilling and punching, shot cutting, galvanizing and dulling. But I will go back to later on about the importance of drilling and punching, why it's also critical in our manufacturing process. When we design a tower as an engineer, we always look for, my strength. What is my yield strength? What's my ultimate? What's the longest? That's anytime we run a software to design it, that's when we look at what's my usage based on my yield strength and this. But we never looked at what are the other requirements that is also going to affect our performance of the lattice tower, which I highlighted here that there are several other requirements that we need to look at, which is a ductility requirement, which is very, very critical for our tower business, because if you don't have a ductility in the steel, then you may have a lot of problems that we have a case study here. Then of course, through thickness, weldability, which is less common, and also this is important here, the fine grain steel for shaping. We do a lot of cold forming, hot forming, and straightening. Which is also critical, that why the grain size should be also looked at it when we consider our lattice tower. Another very important aspect of requirement is toughness. It's very, very critical for lattice tower business. What is toughness? I will go into a little more detail on the toughness. The toughness is the resistance of the material to a brittle fracture when it's stressed. It's pretty standard. It is modified. It is defined as the amount of energy per volume that a material can absorb before rupture. Like foot bond, how much foot bond at a certain temperature. And it depends upon the several parameters here. Temperature is one of the main factors. So material lose their strength with decreasing temperature. So I'll go back here with a little slide back and forth. So if you look at this one, how the temperature versus this one. So at lower temperature, the steel is really losing their toughness. Then also it depends upon influence of loading, how you're loading the towers. And higher the loading, the lower the toughness. And you go back again, then you see that for static load and dynamic load, with the temperature and how it affects the performance of the toughness. Then the grain size. Finer grains are more resistant to brittle fracture, which is common when the grains are more compact, then obviously it gives more resistance to toughness, and that's what, if you have a better compact grain size, then you have better performance. And the last one is cold forming. As you know, when you do any cold forming, you're increasing the yield strength, but at the same time your ductility decreases, which shows here that you're increasing additional. So these are the very important aspects when we consider. And since our steel practice or steel making process has changed, the mill will not care about anything unless you say what you want. Mill will just care about this one. What's your yield? What's your tensile? What's the percent? So toughness is very critical. We talked about that. Now, in normal type of failure that you have when you lack of toughness, then one of the normal general failure that you would notice is the brittle failure. Of course, when the ductile steel, then you have ductile failure more, that you all know that shear, slipping, and toughness and dull kind of a finish that you'll see. But most of the time, lack of toughness, you'll see that brittle failure more, which is cleavage, decohesion, and brittleness and shining. That's the, you will see. So there was a case study done, and Clinton and Waugh was involved, and we tried to put this case study to just to get the prove that why toughness or brittle fracture consideration is very important in our design aspect. So this case study was done for 500 kV transmission. The grade of the steel was A572 grade 50. It's hardwood galvanized and dull. And if you can look at the failure mode, you can see that the started here and going along the edge and all through the bolt holes. So based on our initial observation, it was brittle crack behavior on members during the construction. That's what they do when they put the construction tight in the bolt, because of the impact loading and start initiating all the cracks. So we start thinking about what could be the possible cause of the failure, that why this has happened, why it didn't happen 20 years ago. So possible cause of the cracks could be a liquid metal embrittlement, which is caused by the attack of molten zinc on susceptible steel. Again, if the steel is not right, when you're putting in a hot dip, it will behave very differently. Then, of course, hydrogen embrittlement, that generally caused by the presence of hydrogen atoms within the crystal structure of metal alloy. So that's, again, could be another possibility. Strain aging, plastic deformation, which also is causing that when you punch your holes, then you create a local stress. That could be another possibility. And then maybe there's something wrong with the assembly of the field direction. So there were a lot of questions at the beginning that we thought could be one of the possible reasons. Then we did a lot of investigation. First, of course, the chemical analysis. We found the chemical analysis, it was 57250. And one thing, it was found that it has a very high sulfur content. Again, going back to the steel making process, the steel mill will always cut short their process. They will try to make sure that how they optimize in profitability, and they add silica is very common to get that oxidation done during the melting process. So of course it has a high silicon there, and also we found that it has a long silicon astringent inclusion. Again, the metal will add something that we don't know. Then also the metallurgical investigation done, basically for fracture examination and microstructure evaluation. And we found that all cracks were initiated, as you saw in the picture, on the bolts were corner and propagated along the holes in a brittle mold. Picture obviously tells us exactly the same. We also found that the gauge line for the holes were parallel to the rolling direction. So again, it's critical that where is the rolling grain direction, that just like in the steel ball, if you want to bend a bracket, you want to make sure that the grain is perpendicular to that one. So but in this case, the gauge line for the holes were parallel to the rolling direction. The fracture was a mixed mode with a brittle cleavage. Again, the lack of toughness. And during the when we did the microstructure evaluation, then we found that several secondary cracks because of the punch. When you punch it, if you punch a thicker material, then you will have a lot of localized stress there. And so we found the secondary cracks near the punch hole when appeared to associated with non-metallic inclusive stringers. Again, we have to be very careful what thickness we punch. And then, of course, it shows the indication of material fracture toughness in the steel members. So there was a lot of test lab done. This particular one we're trying to find out is that, we did a Sharpie in a longitudinal direction and transverse direction and the performance. So if you see that, this is the ductile to brittle transition temperature. And the steel member had less ductile temperature at room temperature that you can see here. And all the specimen with the notch, either L notch or T notch direction, it has a brittle cleavage mode of this. And this is most of the common, if you don't have a Sharpie, you'll see that kind of thing. One thing you notice here that you have a better performance with the red one is in the T notch, but normally we say a longitudinal direction notch that we have already. Now, this is also critical that if you look at here, if you look at this one, say aluminum keel versus silicon keel, and you can see Sharpie performance, aluminum keel has a higher performance than the silicon keel. Again, it's very critical that what percentage of silicon that steel mill will add or what we define there. This one is also very important that when you do a Sharpie, when you galvanize it and non-galvanize it, so you can see the performance here, the red one is the galvanized, drops big time. So again, galvanizing also affects the Sharpie of the material performance. This one was done as a normalized, which did a lot of sampling, and based on the sampling, we're trying to find out that if we don't order a steel with our Sharpie, and with the Sharpie, what kind of mill will give you. So if you look at here, with our Sharpie is red, and if you don't say anything, sometimes it comes to default, but if you look at the percentage of default is 10 to 20 foot-pound, which is 45%. But when you say, I need to have certain value, then middle will shoot for the higher value. And then you look at it, you get by default, you ask for 15, but you get a default of, what happened? Something impressive. Oh, sorry. So the middle will give you, by default, if you ask for 15, they shoot for always higher value, and you can see that it comes with 70 to 80s, which is pretty good. Then this is also a grain size based on the ASTM grain that we did, trying to find out. So it just gives an example that higher the grain, the better the Sharpie that we'll get. So results of investigation was that the cracking was attributed due to the presence of a layer of plastic deformed metal at the punch hole and shear surface of the galvanized steel members. Punch hole location acted as an initiation site for the formation of cracks. All materials should have a higher Sharpie value, and of course, it should be, if you have a higher thickness, the material should have a draw rather than punch. When I was doing the investigation, I called a couple of my friends, and I found one of my friends I used to work in Midwest. They sent me a picture, and they had a very similar failure recently. I'm not sure when or which place, but if you look at the behavior again, this is a brittle rupture. And you can see that the tower failed, and it just like knocked off. Here's some more here, you can see that. And of course, this was not energized, all strong, but not energized. There was no life-threatening anything, but you can see that there was 4 or 5 towers was involved in that situation. So going back to the history, I mean, if you look at the history of the Sharpie, this is not a new for us. During the World War II, remember that we had a lot of, we lost a lot of ships, and that's time it was realized the importance of Sharpie, why Sharpie is important when you weld something or an employee. That's the time we start thinking and being more careful about steel that when we order it, what kind of Sharpie that we need to put it. So we did a lot of research and come up with the value that what should be. I talked to several people in the steel industry about where we come up with a 15-foot-pound and -20 in the steel pole. Again, there is no certain guideline, but everybody has different opinions. Somebody says the ice, put the steel in the ice, we come up with this one, then we put this one. So again, this 15-foot-pound and -20 in the steel pole came is working pretty good. So why not we use for our own lattice tower? And this is a specimen. So conclusion I made here is that in the modern scale is a continuous cast process with a scrap-based recycled material. For the reliability of the structure, it's very important to specify the mechanical properties, ductility, toughness, through thickness, and of course, the silicon content that it should be. Right now, our current standard, 1097, is not mentioning anything about the Sharpie, which is very critical for our performance. Ours is Sharpie and the silicon also should be mentioned in that aspect. What I'm recommending here is that if we have a set standard for poles, the 15-foot-pound -20, we're using it, nobody asks questions, millage, okay, why not we use the same for lattice towers, the same steel, same performance? Or why not we investigate something that we feel comfortable, what is that too stringent? Or maybe we need to find for lattice that what value we need to consider. One thing we remember that steel mill always going to object for anything that we ask for, but once they start doing the practice, one standard set of guidelines, then they keep doing it. So it's just a matter of coming up, what's the standard, steel standard for lattice tower that we will need for our lattice business, and then what guideline the mill needs to follow. That will make everybody's life much easier. And then mill will follow the same guidance rather than now everybody has a different opinion. I don't need Sharpie, I need Sharpie, this is the number, that's the number. And also silicon percentage is very critical because I didn't talk about here the silicon, but having a silicon like in the pole, we say less than 0.05%, which is pretty standard again in the spec. That mill is spec and everybody's spec the silicon content would be. But lattice tower, they know if you go with ASTM 572, it will tell you silicon maximum is 0.4. If you go that, then it's a totally different result. So There should be a guideline for the silicon also, what should be considered for lattice tower, to make sure that the appearance and other things that involved for the static purpose should be also addressed, rather than just take it for the mill grinder, that mill will give you 0.4%, and then you have a burden on the manufacturer to try to give them that your process has to be improved because something is missing. The main issue here is that the steel has to be right composition, right properties to make sure that you meet the structural requirement, and then you meet the delicate requirement or galvanized requirement. So this is very important that as a group or a standard, I've been requesting to the tower committee to address this concern that we need to have somehow address the Sharpie and silicon just like in steel poles. So that way, as industry standard wise, we have a common standard, and that will help as a manufacturer, help as a customer, as a consultant, and the steel mill to be on the same page. That's what I conclude. Thank you.
Questions?
AJ, historically, the good fabrication practice has been very important to avoid some of this, especially when it comes to the thick members. It looked like you had a leg member that they can get pretty thick, inch on it, and it was always known that you have to drill those rather than punch. And it looks like now with maybe some new manufacturers and some new processes, if they're starting to punch these, then you definitely have a problem. And then you either have to look at the Sharpie or you have to look at the good fabrication or manufacturing practice. Have you seen anything in thinner members? Have you done any testing like for members that are thinner, or the ratio between the holes and the thickness?
Yes, we did a lot of, we call it bend test, trying to get a bend test to Sharpie and non-Sharpie. Even the thinner material, like half inch, kind of a standard. And based on what we did in the bend test, finding that, bend test, you get to go a certain ratio, and slowly you measure your deflection, the depth. And we found that a Sharpie material versus non-Sharpie, it performed very well if you have a Sharpie in the material. We did that at bend test. So it's a combination of your manufacturing practice, as you said, the drill versus the punch. Then also the combination of what ductility you have, the toughness you have in the steel, because it's definitely going to help. Again, you saw that galvanizing steel perform very differently than the black steel. So when you're galvanizing the steel, you are not disturbing the properties, and then you have different sharpness. So you're creating more brittleness in the structure, in the member. So having a certain Sharpie is very critical when we do either galvanizing and punching, or you do any kind of material handling or some of the construction side. So it has to have very important. And then also it helps in, there's two ways to look at it. One is the temperature variance, where you have a minus sub-zero temperature, the Sharpie comes into play. And another is aspect of the manufacturing side, the hole punching and all those things.
I'd like to add one thing. As a result of AJ's study, what we're doing at Edison is we're including basically the results of the study in our specs for steel lattice towers. And the way that we're doing this is, when we order steel for steel lattice towers, we're either ordering A572 steel with Sharpie or A709 steel. And 709 steel is basically 572 with the Sharpie values included. The other thing that we're doing to mitigate the brittle failures is we're requiring that for all lattice members greater than 1/2 inch in thickness, that it be drilled. So any holes need to be drilled greater than 1/2 inch thickness, and any members that are thicker than 1/2 inch has to be saw cut rather than, clipped, or sheared. Yeah. So that's what we're doing, and that's a result of the study that AJ had done.
Can I just follow up quickly? One of the questions you had in the beginning was, what has changed from the old ways of doing it to the, I just didn't get that part of it. What do you think is mainly happening with some of the new steel?
And steel, right, that's a very good question. And what has happened that, I'll go back quickly to the slide here, make sure that I can go back here.
Could you repeat the question?
Yeah, the question is, what have changed in the steel making process? What was done earlier, like 30 years ago, and what has been done right now? In the past, when the steel was doing with the mineral ores, so you were getting an ingot as almost like a pure steel, not impure, less impurity than you do. You were casting the steel with the mineral ore, and all the ingots were perfectly pure. So you had a default combination of your chemistry in that when you do a mineral ore. But right now, the steel, especially for the angles, is a recycled material. So they get all the recycled material, they add all the extra things like silicon and other things to just give you the grade of steel that you want. But there are a lot of things that add is affecting the performance of the steel that we should be specifying. That's the biggest change that you see, that this machine here is all electric arc furnace. With electric arc furnace, they dump all the scrap material, they burn it, and then add all different things and get you steel. So this is the way is now steel angle being rolled. And this will not give you any guarantee that how pure the steel is and how good chemistry the steel is.
My question actually relates to that. Plates, like gusset plates, versus the angle versus the bolts. Is it more difficult to get the type of specs that you want for the material for the rolled shapes like the angles than plates and bolts?
Yes. Normally,
Repeat the question.
the question is the grade of steel and how common is like plate steel versus the angle steel, and how difficult to procure the steel from the mill. Normally, the process making is very different. So plate making, if the steel mill is making the plate, may not make the angles. It's totally different rolling setup, totally way of their processes. So you may have, plate is very common now that everybody uses plate in industrial buildings and stuff like that, but the structural steel for a lattice tower, you have only 2 or 3 choices because they have to have a totally different process. So right now, you buy from Nucor or a couple of more in the U.S., or you can go overseas to get that steel. So it's very critical for our industry that understanding that limited supply, limited choice of suppliers, and we need to work in a way that develop a standard so that they have one set of standard for always. When we need a tower, they say, I need this much ton, this much size, give me. They know pretty much this is the standard. I say, A307 standard, they understand that a Sharpie, that a silicon, and they'll just do it. That's how it should be our goal.
Okay, we're out of time, and it looks like there's quite a bit of interest. So, AJ, are you and Clint going to be around today?
Yes.
So, could you hold your questions for these guys in a bit and give them a hand? And appreciate